Chapter 17 is called Introduction to the Physics of Hearing, and it starts by saying that if a tree falls in the forest and no one is there to hear it, does it make a sound? So sound is a pressure wave in the air, but sound is also something that humans perceive using their ears. So let's check out their little video.
Sound is a wave created by a vibrating object that is transported through a medium like air. When produced as music, vibrations have rhythm. Though not necessarily able to hear audible sound, the deaf and hearing impaired can feel vibrations and enjoy music. The string down in the middle. The length of the string equals one wavelength. The third harmonic.
Their video today is surprisingly highbrow. It's not about sports, and it's not about guns or anything, or the gridiron. It seems to be about classical music. So that's really pretty cool. It's overproduced, for sure, but I think it's a bit different. They talk about shattering a glass with a sound wave, so sound carries energy. And when you're looking at that stringed instrument, for example, there's two things that happen. First of all, there's a standing wave on the string, so the string moves back and forth, and that would happen even if you were on the moon in a perfect vacuum. But here on Earth, when you're in air, that back and forth motion produces compressions and rarefactions in the air, where compression is high pressure, rarefaction is low pressure, and those changes in pressure propagate outwards away from the string at 340 meters per second, and that's sound, because later it hits your ear, and the high pressure and low pressure pushes and pulls your eardrum, and that vibration gets transmitted into electrical signals in the nerves of your inner ear, and then gets carried to your brain, and that's how you hear. Section 17.2 is the speed of sound, frequency, and wavelength. So certainly the speed of sound is equal to its frequency times its wavelength, but it's a fixed number. So remember, this on the left is fixed. So if the frequency goes up, the wavelength goes down, and if the wavelength goes up, the frequency goes down, etc. So another way of putting it is that if you know the frequency of the sound, you can compute the wavelength because the speed is given. So the speed is 331 meters per second in air at 0 degrees Celsius. Different substances also can carry sound waves. You can have sound in carbon dioxide, has a lower speed of sound. Pure oxygen, a helium environment, hydrogen environment. So hydrogen at 0 degrees Celsius, the particles move very fast, and so you get a higher speed of sound. Same with helium. This is why if you breathe helium, you end up with a Mickey Mouse voice, is because the speed of sound in helium is much greater than the speed of sound in air, and so the standing waves in your larynx have a much higher frequency. Liquids and solids tend to have a high speed of sound, except for rubber, but most things that are solid like lead, aluminum, steel have very high speeds of sound. This equation 17.2 gives the temperature dependence of the speed of sound. It is proportional to the square root of the temperature in Kelvin. So you have to convert temperature in Celsius by minusing 273 degrees, and you get, by adding 273 degrees. So 0 degrees Celsius is 273 degrees Kelvin. So 273 over 273, square root of 1 is 1. That's how you get the 0 degrees Celsius speed of sound. And then you can compute at 20 degrees Celsius room temperature, you'd use 293 over 273, multiply it square root, and you get 343 meters per second for 20 degrees Celsius. This equation, I'm not sure why they add this here. This is the RMS, root mean squared velocity, or average speed of air particles. I guess they're just saying that there's a square root in there, and so square root of temperature. So they're relating the speed of actual particles in the gas to the speed of sound, which is how fast a pressure wave travels, and they're sort of related, so you don't really need equation 17.3. This is just showing that sound waves and measuring the delay time for an echo of a sound wave can be used to measure the distance to something that's creating an echo. There's an example here. Calculate the wavelengths given frequencies. Well, you need the speed of sound, and so you can calculate the speed of sound based on the properties of the medium, and then use this general equation, the speed of a wave equals its frequency times its wavelength, to calculate the wavelength. And the last section is about sound intensity and sound level. So you may have heard of decibels, that when there's a lot of traffic, it might be 80 or 100 decibels, and it can cause ear damage. So what we're talking about here is intensity. Intensity is the power divided by an area, cross-sectional area. So the units for intensity is watts per meter squared. And remember, a watt is a joule per second. So you're talking about how many joules of energy per second pass through a particular cross-sectional area. That gives you the intensity. And it turns out, they don't show that here, is that a sound wave is really a change in the pressure. So the pressure goes up and down, above and below the ambient pressure. And the amount that it goes above or below ambient pressure is called delta P in pascals. So if you know the delta P, the amplitude of a sound wave, then this equation gives you the intensity. So higher changes in pressure give you a higher intensity, and there's a square here. So delta P squared divided by 2 times rho, which is the mass density of the medium in kilograms per meter cubed, and VW is the wave speed. And this diagram, I don't know who the artist is, but basically a small, so this is your delta P. Small amplitude sound gives a small intensity. Larger amplitude sound gives a larger intensity. Okay, so intensity is a real thing in physics, watts per meter squared. That's all you really need to know. But there is an alternative way of expressing intensity that's used by a lot of municipalities, and it is called sound intensity level beta. And it has this complicated looking equation. It's 10 times the logarithm, base 10, of the intensity divided by I0. So the basic idea is that the greater intensity of the wave, the greater the level, and sound intensity level is beta. But it's related to a logarithm. So essentially, it's just a more convenient way of expressing intensity, I guess, for sound waves that humans hear. So if you plug in these different intensities in watts per meter squared, you can figure out the sound intensity level. So the quietest sound that a human being can hear carries about 1 times 10 to the minus 12 watts per meter squared of intensity. It's called the threshold of hearing. That is also this I0, so the logarithm of 1 is 0, so that sound intensity level is 0. 10 times that intensity is like the rustle of leaves. You can hear it pretty easily, but it's still very, very quiet. That carries 1 times 10 to the minus 11 watts per meter squared. If you plug that in here, you get the log base 10 of 10, which is 1 times 10, you get a beta of 10 decibels. And it goes all the way up like that, so that every time you multiply the intensity by a factor of 10, you add 10 to the decibel level. That's a property of how logarithms work. And there's something called the threshold of pain, which is 1 watt per meter squared. It's like a loud rock concert. You can kind of tolerate it, and as long as you're not there for too long, it doesn't cause permanent hearing damage. That turns out to be 120 decibels. But you can even go above that, of course, to the point where over a short amount of time you can do permanent damage to your ears. And they give you some ratios. If you have an intensity ratio, it turns into a sound intensity level difference. So if a sound is twice as high, that means it'll be about 3 decibels higher. If a sound is 5 times higher intensity, then it'll have a decibel level that's 7 decibels higher. And again, if you increase the intensity by a factor of 10, you increase the decibel level by adding 10. There are some examples of doing that, which I would suggest that you go through. Section 17.4 is Doppler effect and sonic booms. So the Doppler effect is all about the frequency you hear compared to the frequency of the source that is moving relative to you. So it's actually something you may have noticed in real life. It's pretty noticeable. Here is a car which is driving towards us. We're sort of off to the side here. But what the guy's going to do is lean on his horn, and you'll hear the frequency change as the car is driving towards you as opposed to away from you. And it's not the horn, it's the Doppler effect. Okay, so what causes it? Well, there's a pretty good animation here. If you have a stationary source and a stationary observer, the red dot here, then as these wave fronts pass by, the same frequency that is emitted will be the frequency that is received by the observer. However, if the source is moving, then these wave fronts will be bunched up in front of the observer and more spread out behind the observer, so that the frequency that the waves arrive when the source is approaching you is higher. However, when the source is receding away from you, the frequency at which these wave fronts arrive is less. And that's the Doppler effect. This animation also shows a source that is traveling faster than the speed of sound, in which case, boom, all of these wave fronts form what is called a shock wave, which gives a sonic boom after the Mach cone passes you. Here are some diagrams, and it's a little hard to see because these aren't videos, but wave fronts are expanding from the horn, and each wave front is a high pressure area, and then between it is the low pressure area. So as these high-low pressure areas pass your ear at the speed of sound, that's the sound frequency that you're going to hear. Well, if the car is approaching you, then maybe second 1 it's here, second 2 it's here, second 3 it's here. At the 5th second, it emits sound which is centered here, whereas back at second 1 it emitted sound which is centered way over to the left. So when these sound wave fronts arrive at the speaker Y, or the listener Y, then she's going to hear them all bunched up, but they'll still be going by the speed of sound until she'll hear a higher frequency. Whereas this person X will hear the sound going backwards. All those wave fronts are more spaced out, and so he'll hear a lower frequency. And it's also true, too, that if the car is stationary and you're running towards it, then you'll pass those wave fronts at a faster rate. You'll hear a higher frequency. Or if you're running away, as the wave fronts are catching up to you, they'll pass you at a lower frequency. So you can get Doppler shift is based on relative movement. And there are two different equations depending if you're moving relative to the air or if the source is moving relative to the air. And you can calculate these frequencies. And the frequency shifts are all pretty low. It's usually just a couple of hertz. But your ear is very sensitive to frequency, so you can really hear these in real life. So these are all for speeds that are much less than the speed of sound. It is possible for some aircraft and very, very fast cars to break the sound barrier. You can go faster than the speed of sound, in which case these equations don't really work. And what you end up with is a cone of sound that expands away. So here's this object that's traveling faster than the speed of sound, and along the edges of this cone you hear constructive interference from many of these expanding wave fronts, and this is called a sonic boom. It's a very loud booming which is created when an object moves faster than the speed of sound. So there's this supersonic jet, and here's a person who can't hear it yet, and here is a person hearing that sonic boom, and then you can hear the jet. All that sound is audible after the jet passes. And section 17.5 is sound interference and resonance, standing waves and air columns. Basically, this is talking about the principle of superposition, which applies to sound waves as well. When you add two sound waves, they will pass through each other, and the resulting pressure will be the sum of the change in pressure of both waves. So, for example, if you have a particular wave and you add it to the inverted wave, you can cancel out the sound. That's what noise-canceling headphones do. There's a microphone on the outside which listens to ambient noise in the room, and then there is some electronics which plays that same sound but inverted, so that at your ear you receive both. You receive the inverted sound and the sound that's surrounding, and the two waves can destructively interfere, and you end up with silence. And another aspect of this interference, we had standing waves before. There are standing waves of sound. So what they're trying to show here is sort of a reflection where you're adding two sine waves. And so you have a tube which is closed at one end and open at the other end, what that can tend to do is to force a node at the closed end and to force an antinode at the open end. I don't really explain it very well here, but remember, for waves in a string, you forced a node at each end, and then you can get different modes of the standing wave with different frequencies forming. With a closed open tube, you're forcing a node at one end and an antinode at the other end, and there are these different modes here. You can have a quarter of a wavelength, 3/4 of a wavelength, 5/4 of a wavelength, etc. And so these are called overtones of standing waves in a closed open tube of air, like a clarinet, for example. Your larynx inside your throat and nose will act as a standing wave cavity for sound waves, which is part of what gives you the sound of your voice. And pretty much all wind instruments do work on this same principle. So a flute would have two open ends, and you get as it turns out, also these different standing waves with integer multiples of frequency of the fundamental. And even the box on a string instrument uses standing waves in air columns to amplify the sound that's coming from the string and give each instrument its own timbre and sound. So hearing is when humans perceive sound. Normal human hearing encompasses frequencies from 20 up to 20,000 hertz. Sounds below 20 hertz are called infrasound. You can't perceive them, whereas those frequencies above 20,000 hertz are called ultrasound. The perception of frequency is called pitch. Musical notes are particular sounds that can be produced by most instruments, and in Western music have particular names. And so, for example, there are 88 keys on a piano keyboard. The lowest one, it's called A0, has a frequency of 27.5 hertz. And so all of these frequencies listed here are the frequencies of various notes. If you go up to a note called C4, that's middle C on your keyboard, that has a frequency of 261.6256 hertz. If you go a little higher, A4, which is the A note just above C, has a frequency which is defined as 440 hertz. That's what all other instruments get tuned to, and it goes all the way up to the 88th key on the piano keyboard, has a frequency of 4,186 hertz. It's called C8. Above that, we can still hear very, very high frequencies, but they're not very interesting musically. So that's pitch. Another aspect of sound is its loudness, which is related to the amplitude of the wave. So a wave is going to have a frequency, and it's also going to have an amplitude. Larger amplitude waves have a higher loudness. Now there's another property of musical notes called timbre. For example, you can play a middle C on a violin. It doesn't sound the same as a middle C played on a piano. And so this has to do with actually the whole spectrum of all the different component frequencies in a particular sound that gets made by a musical instrument. There is a pitch, which is related to its fundamental frequency, its repetitive frequency, but what's composed in the whole spectrum does get picked up by your ear, and that's what gives us the timbre of the sound. Now, this graph, so what is this? This is sound level versus frequency. So these are called Fletcher-Munson curves, and what they do is they describe the sensitivity of the human ear. So for each curve, many people surveyed that listen to different frequencies believe them to be about the same loudness to our ears. So, for example, a 1,000 hertz tone at 0 decibels sounds about as loud as a 200 hertz tone at about 23 decibels. So the lower and lower frequencies, you have to turn up the sound level in decibels to make them sound the same as the place where our ears are more sensitive. Our ears are most sensitive somewhere around between 3,000 and 4,000 hertz. And then if you, again, go to higher and higher frequencies, our ears, again, are less sensitive because you have to turn up this sound level in decibels in order to get it to sound the same as it did at 4,000. This is the intensity level of normal speech, around 60 decibels, and sort of a a range of frequencies between about 125 and about 3,000 hertz. These are just showing you that different people lose their hearing at different frequencies. So often the higher frequencies are lost first as people age. This is showing a diagram of the inner ear. So sound waves enter from the left and they cause the eardrum to oscillate as the pressure increases and decreases. There are then these three little bones in the middle ear which amplify the pressure of those oscillations, and they do that through various pivots. So the three bones are called the hammer, anvil, and stirrup because they're named after, they kind of look like those shapes. And here's a schematic diagram showing the pressure variations of the eardrum spread over some area, and then these pivots which amplify, using mechanical advantage, the pressure that is output onto the oval window. And the oval window is connected to the cochlea, which is the part of the inner ear which actually converts the sound waves to electrical signals, which then go down the cochlear nerve and into your brain and then get perceived as sound. And this is a little description of cochlear implants. So if some part of your middle ear has been damaged and you can no longer hear, there are ways of accessing the cochlea directly and transmitting vibrations to them and restoring someone's hearing. And the last section we'll be studying is about ultrasound. So any sound with a frequency above about 20,000 hertz is defined as ultrasound, and it has many uses. Ultrasound carries energy, and that energy will be absorbed by any medium that the ultrasound is traveling through. And this energy can be used, for example, to destroy tumors inside the human body with very high intensity ultrasound. That's medical therapy or treatment of cancer. You can also use ultrasound in diagnostic. If you turn down the intensity and are looking at reflections of ultrasound, you can make images inside the human body. And the quantity they introduce here is called acoustic impedance. Impedance is related to the speed of sound in a medium. So the speed of sound is different for different kinds of materials like air, water, blood, fat, muscle, bone. And when there is a sudden change in the impedance, you get reflected waves. And there's a reflection coefficient is the ratio of the intensity of the reflected wave to an incident wave. So what you do is you put a speaker on someone's tissue, let the ultrasound waves go into the person's body, and then you have a microphone which picks up the reflected ultrasound waves, and you can create an image from those reflected waves of what's going on inside the body. And here we see a little baby inside a pregnant woman. And this can be done in 3D with computer rendering. And when the impedance boundary is moving relative to the microphone, you can get Doppler shifted ultrasound, and you can find the velocity, for example, of blood flow through a vein or artery. My name is Jason Harlow, and I hope you enjoyed this video. If you have time, please fill out the feedback form on my Google Forms available in the description to this video. There's also a link to the Google Classroom where there's a public discussion forum and a place where you can ask me a lot of questions. Also available as a link in the description to this video. I look forward to hearing from you. Take care.